Welcome to this lecture. This is the second lecture of week 8. We have been discussing about central limit theorems. So, this is a special case of weak convergence of random variables. So, in this lecture we are going to look at some other nice results involving weak convergence and also discuss some further applications of the central limit theorem. So, let us continue the discussion using the lecture notes. All right. So, as always we are going to look at a fixed probability space omega f p, and all the random variables that we considered, we will assume that it is defined on this specific probability space. Now, recall first that we have discussed earlier in proposition 4 of week 6 that if we consider the weak convergence of random variables, but to a constant or degenerate random variable, then this is actually equivalent to the same convergence in the sense of convergence in probability. So, in general, convergence in probability is stronger than the notion of weak convergence. However, if the limit random variable is a constant or a degenerate random variable, then the same convergence is actually equivalent whenever we are considering the weak convergence or the convergence in probability. Now, in this setup we look at a very interesting result called the Slutsky's theorem. So, the idea is this: we fix some scalar c in the real line and we are going to treat this c as a constant or degenerate random variable. Now, assume that we have two sequences of random variables. The first one x n converges to some random variable x, and the other sequence y n converges in the sense of weak convergence to this constant or degenerate random variable c as n goes to infinity. So, here as pointed out, the convergence of y n's in the sense of weak convergence is actually equivalent to the convergence in probability to the same limit. Now, if you have the information that you have this specific type of convergences of x n as well as y n, then the statement says that the following weak convergences hold. So, let us see them one by one. So, the first statement says look at the random variables x n plus y n, and as n goes to infinity they converge in the sense of weak convergence to x plus c. Then the second statement says look at the product x n times y n, they converge in the sense of weak convergence to the random variable c times x. So, here we are treating c as a random variable as well as a scalar. And finally, if c is a non-zero scalar, then x n divided by y n, these random variables as n goes to infinity converge to x over c as n goes to infinity in the sense of weak convergence. So, these are pretty useful in our calculations, and that is the importance of this result. Now, these three results are actually proved using similar methodology, and just to show the idea we discuss the proof of the first part only. So, let us see how we can show that if the two sequences converge as stated in the result, then x n plus y n, how do they converge to the random variable x plus c. So, what we now have to focus on is the distribution function of the random variable x plus c. So, let us set up certain basic notations. So, suppose f subscript capital X denotes the distribution function of capital X, then let us look at the distribution function of capital X plus small c. So, if you look at it through the definition, we have to look at these probabilities. However, these can be reduced to a probability involving the original random variable capital X, and therefore, we can rewrite it in terms of the distribution function of capital X evaluated at small x minus c. So, therefore, what we are saying is that for all small x in the real line, the distribution function of capital X plus c is actually can be written in terms of the distribution function of capital X So, evaluate the functions at the point x minus c. So, that is all we have to do. Now, we need to establish the corresponding pointwise convergence of the distribution functions to the limit value of f x plus c at that point, but only for the continuity points. So, that is the definition of weak convergence we are recalling, and that is what we want to establish. So, suppose small x is a continuity point of this distribution function of capital X plus small c. Then if small x is such a point, then immediately we will conclude by the relation between f x and f x plus c that x minus c, the small x minus c is a continuity point of capital F x. Now, let us look at f of x n. So, these are the distribution function of x n's, and suppose we denote by g n the distribution functions of x n plus y n. So, our interest is to look at the limit of g n's. So, let us see. So, first we look at certain estimates involving g n. So, for any epsilon positive, look at g n of small x. So, this is by definition the probability that x n plus y n is less or equal to small x. Now, rewrite this event as the union of two disjoint events, and therefore, we will have by total probability law that we have to look at the probability of these two events now. What we do is that on one hand we introduce the condition that mod y n minus c is less than epsilon. On another hand, I look at the other complementary event where mod y n minus c is exceeding epsilon. So, we do not change the first part here. So, we are essentially splitting the original event into these two parts. Now, observe that if we focus on only the first event that is given to us, that is actually a subset of this event. So, this is immediately true because we have here certain estimates involving x n plus y n less equals to x, and we also have that y n minus c falls between epsilon to minus epsilon. So, if you combine them together, you will have this upper bound for capital X n. So, therefore, the first event in question is contained inside this event here, and therefore, the corresponding probabilities will be less equal to the probability of capital X n less equal to this quantity. And let us now look at the second event. The second event is a subset of y n minus c exceeding epsilon. So, therefore, the corresponding probabilities are also dominated by this. So, therefore, we have obtained an upper bound for g n of x. Now, in a similar way, we can now start with these specific distribution functions f of x n evaluated at small x minus c minus epsilon. If you start with this, we can do a similar argument and end up with this kind of an upper bound. Please check this, this is just using a similar argument. But now, let us use both of these upper bounds in our argument. Now, so far we have not put any condition on the epsilon, but now note that we can choose epsilon positive such that x minus c plus minus epsilon are actually continuity point of f x. So, here note that we have assumed that x minus c, that is a continuity point of f x, but since f x itself is a distribution function, its continuity points are dense in the real line, and in particular away from that point x minus c, in the immediate neighborhood we must find other continuity points. So, therefore, we can easily find points of this type which are x minus c plus or minus epsilon, which are also continuity points of f x. So, here we can choose these epsilons to be in arbitrarily small. So, this is simply using the fact that the continuity points of f x are dense in the real line. Now, if you use this fact, then we observe this set of inequalities following from the estimates that we have already obtained. So, what we do here is that we look at lim inf of g n's. So, here note that this follows from our second inequality that we have obtained. So, let us just go back to the second inequality here. So, if you let n go to infinity, on the right hand side if you look at liminf, on the second term here actually we have an information that y n's converge to the constant random variable c in probability. So, therefore, these terms go to 0 as n goes to infinity. So, that is what we are using to write this inequality that we have seen here. The liminf of this sequence g n of x is dominated from above by the lim sup of the same sequence. So, that is what we write. But now again we go back to the earlier estimate involving g n, and again using the fact that y n's converge to the constant random variable c in probability, we will end up with this upper bound. But now we can appeal to the arbitrariness of the epsilon, that such epsilons can be chosen arbitrarily small. And since x minus c now is a point of continuity of f x, what we actually now conclude is that by taking epsilons arbitrarily small, we must have first of all these kind of equalities here, that lim sup and liminf must match. So, therefore, the limit exists and the value is exactly f x evaluated at small x minus c, but that is nothing but the distribution function of x plus small c evaluated at small x. Here small x is a point of continuity as we have assumed for the distribution function of the random variable x plus c, and therefore, we have obtained our result that for all such continuity points the corresponding convergence, pointwise convergence of the distribution functions hold. And therefore, what we conclude is that x n plus y n, these random variables converge weakly to the random variable x plus c. So, here our assumption is that x n's converge to x in distribution, y n's converge to c in distribution, and therefore, what we are claiming now is that x n plus y n converges in distribution to x plus c. So, other results as we have said follows using similar methods, and we do not go through identical arguments to save space. Let us now focus on some application of the Lindeberg-Levy central limit theorem that we have discussed in the previous week. Now, here the idea is we are going to use the Slutsky's theorem and we are going to connect the central limit theorem to the weak law of large numbers. Remember that we have mentioned in note 16 of week 7 that our original motivation for looking at the central limit theorem was this, that we wanted a rate of convergence result for the weak law of large numbers, and we ended up with the central limit theorem, that is Lindeberg-Levy version. Now, what we point out is that a result where the convergence is stated together with a rate of convergence, which is the type of result CLT is, we should actually treat it as a stronger form of result than results where there is no rate of convergence. So, if you know that certain convergence holds together with a rate of convergence, that should be treated as a stronger result. What we actually are going to discuss is that in the Lindeberg-Levy form of the central limit theorem, the weak law of large numbers can be shown as a consequence. Let us see. So, we start with the Lindeberg-Levy central limit theorem and recall the statement. So, that statement says that if I have a sequence of independent and identically distributed sequence of random variables x n, look at the corresponding sample mean x n bar. Now, here we are looking at this identical means. So, we subtract this out and we rescale by the corresponding standard deviation of these random variables x n, which are also same, and by our assumption this sigma is positive. Now, the Lindeberg-Levy form is simply saying that square root n multiplied by this quantity converges to a normal 0 1 random variable in the sense of weak convergence as n goes to infinity. So, this is the result, but now appeal to the Slutsky's theorem. First, observe that if we look at this sequence of real numbers sigma by root n, then as n goes to infinity they converge to 0. So, by appealing to Slutsky's theorem, look at a product of this kind. So, here the product actually is nothing but the difference between x n bar minus the expected value of x 1. So, now by the Slutsky's theorem, the first term here converges to 0. So, that we know about. We are treating sigma over root n as random variables, but these are also degenerate and converging to 0 as n goes to infinity. Convergence in the sense of weak convergence as well as in the sense of probability, because the limit random variable is degenerate. Finally, by the Lindeberg-Levy central limit theorem, the second term converges to a standard normal random variable z. But now, the product random variable is actually now again identically 0. So, therefore, this overall weak convergence is actually a convergence in probability, right. That is what we had discussed earlier in proposition 4 of week 6. And consequently, we actually restate this observation in this form that x n bars converge in probability to expected value of x 1 as n goes to infinity, which is exactly the weak law of large numbers we have considered for IID sequence of random variables earlier. So, the only additional assumption that we are considering in the Lindeberg-Levy central limit theorem is that the fact that these random variables have finite variance which is positive. So, with the appropriate additional assumptions, what we are actually saying that this central limit theorem is a stronger result than the weak law of large numbers. That is what we expect, because the central limit theorem is actually giving us a rate of convergence for the weak law of large numbers, and hence should be considered as a stronger result, and that is what we are verifying through the application of Slutsky's theorem together with the Lindeberg-Levy central limit theorem. All right. So, now we look at some further discussions involving this Slutsky's theorem. So, the first point that we will highlight is that the following variant of this Slutsky's theorem that we are considering is often useful in practice. So, what we do is this: we look at now two sequences of random variables x n and y n, such that x n converge in the sense of weak convergence to a random variable x, and x n minus y n converges to the degenerate random variable 0 in the sense of weak convergence. Then, if we go back to the earlier setting, the addition of x n together with minus of x n plus y n, that will give you just y n. So, therefore, that converges in distribution to x. So, this is just a variant of the result that we have already seen in the Slutsky's theorem above, and this is often useful because if you want to establish the convergence of y n to x, then find a somewhat close sequence x n in the sense that x n minus y n converges to 0 in the sense of weak convergence, and establish the relevant converges for the x n. Then the statement will say that y n also converges in the sense of weak convergence to x. So, this is often useful in practice. In fact, this version that we have just stated actually can be generalized to random vector setting also. So, suppose you have two sequences x n and y n of d dimensional random vectors with this property that x n converge weakly to x, and x n minus y n, the norm of that, converge to 0 in probability. Again, remember, this is equivalent to the notion of weak convergence. So, here the norm that we are considering is the standard Euclidean norm on R d. So, x n minus y n are R d valued random vectors. So, if you consider the norm, they are going to give you real valued random variables, and for that setting we are asking about the corresponding convergence to 0 in the sense of convergence in probability or equivalently in the sense of weak convergence. Then the result states that under the assumptions we must have y n converge weakly to x. So, this is also useful in the random vectors setting. Now, we go back to some of our earlier discussions that we conducted in week 5. So, this was pointed out in note 2. So, the idea that we have discussed there in week 5 earlier is that we were considering sequences of independent random variables. Then for such sequences we had looked at the almost sure convergence of the corresponding series. And there we had discussed about these important results such as the Kolmogorov 0-1 law, 2 series theorem and the 3 series theorem. However, recall that in the 3 series theorem what we have considered was that there we considered 3 real series and we have stated that the original series of random variables converge almost surely if certain specific 3 real series converge in the sense of convergence of real series. Now, this condition was stated to be equivalent. Earlier what we have discussed in week 5 was the sufficiency part, but now we are going to see the necessity part of it, and this will involve certain application of the Lindeberg form of the central limit theorem. Let us see. So, we recall the setup from week 5. So, the main result that we are discussing is the Kolmogorov 3 series theorem, which was theorem 2 of week 5. So, the setting is this, that we have a sequence of independent random variables such that the corresponding series converges almost surely. Then we want to show that for all C positive, these 3 real series converges. So, here what we are looking at are these truncated random variables. So, here these truncated random variables are defined in this way, that for any such C and n positive integer, we are looking at this kind of a random variable, that is what we denote by x n superscript C. So, here we are simply truncating the original random variables, and therefore, these truncated random variables are all bounded by C. So, here what we are looking at are the expectations and the variances looking at the corresponding series. They should converge, this is the necessary condition, and finally, we would also like to show that these kind of probabilities are also summable. So, we would like to establish that these 3 series, the convergence of that is a necessary condition for the almost sure convergence of the series of independent random variables. So, let us see the proof of this. So, what we do is that we fix some C positive. Now, first note that since we are given that this series converges almost surely, in particular we will immediately have that limit of x n must be 0 almost surely. So, this is just a necessary condition. Consequently, what we can look at outside some appropriate null set, what we are going to have is that by this specific constant, the modulus of x n should be upper bounded. So, this is simply using the fact that limit of x n is going to 0. So, now this n that we are looking at may depend on the choice of small omega, does not matter, but what we are saying is that for every such omega coming from the complement of a null set, for large enough n, x n matches with the truncated random variables, and therefore, what we immediately will conclude that since the original series of random variables converge, then the truncated random variable series also must converge for all such omega, because in the convergence of a series the first few terms does not really matter. So, therefore, what we ended up having is that the corresponding series of truncated random variables converge in the sense of almost sure convergence. But now, we appeal to the Borel-Cantelli lemma second half, which we have discussed earlier in week 2, and we will conclude immediately from that the probability of modulus of x n exceeding C, those probabilities are summable, and therefore, we have the convergence. So, this immediately follows by a immediate application of the Borel-Cantelli lemma second half applied to this independent random variables x n. So, one of the conditions that we said to be necessary we have established, but now let us look at another condition. So, suppose if possible that these series constructed using the variances of the truncated random variables does not converge and actually diverge to infinity. Suppose this happens, then what happens is that if you look at the corresponding truncated standard deviations, which are the variances of the truncated random variables, then they are going to infinity as n goes to infinity. We are going to use this fact in our argument. Now, here you note that if you now look at these centered random variables, that we look at first x n truncated at C, subtract out the expectation of these random variables. So, these are all centered random variables, but now they are also uniformly bounded. Why? Because you note that x n truncated at C minus expected value of x n truncated at C, that can be dominated by modulus of x n truncated at C plus modulus of the expected value of the same random variable, but all these quantities are actually dominated by C. So, therefore, we have the bound given by 2 C. So, this number is independent of n. So, therefore, all these random variables are uniformly bounded. Now, we appeal to a special case of the Lindeberg's condition that we have discussed earlier in remark 1 part B, and as a consequence we will claim that this form of the central limit theorem holds, that we look at the summations involving the truncated random variables and rescale them by first subtracting the mean and dividing by the corresponding standard deviation. Then as n goes to infinity, we must have the convergence to a standard normal random variable in the sense of weak convergence. So, this is just an application of the observation that we have made earlier. Now, here what is happening is that we have pointed out that since this truncated series of random variables converge almost surely, then the corresponding sequence of partial sums must also converge almost surely, and as a consequence what we will now conclude is that these sums involving the truncated random variables scaled by the standard deviations must converge to 0 almost surely, as by our assumption these standard deviations actually go to infinity as n goes to infinity. Consequently, what we are having is that since this convergence, the final statement that we have made in the sense of almost sure convergence, then the improbability convergence also holds, and as a consequence for all epsilon positive we must have this fact that S n divided by the corresponding standard deviation away from 0. So, that is this modulus quantity by this epsilon number, that probabilities must go to 0 as n goes to infinity. So, this is simply using the fact that almost sure convergence implies convergence in probability. But now, what we are actually saying is that we have two kind of convergence statements involving the capital S n truncated at C. So, on one hand we have the central limit theorem type statements that the truncated random variables centered and scaled appropriately converges to a standard normal random variable as n goes to infinity. On another hand, we are saying that if we rescale these sums of truncated random variables rescaled by the corresponding standard deviation, they actually converge to 0. Now, these two facts are actually contradicts each other, okay? And we have arrived at a contradiction which is now essentially contradicting the conclusion of the Lindeberg's form of the central limit theorem. So, this contradiction actually arises from our original assumption that the series formed by the variances of these truncated random variables do not converge and they diverge. So, that was the original assumption from which we have arrived at a contradiction. So, we must have made a wrong assumption and therefore, we must have the convergence of these series. So, finally, we are left with the establishment of the series convergence for the corresponding expectations of these truncated random variables. Recall from our earlier discussions involving the two series theorems, which was essentially the theorem 1 of week 5, that the condition on the summability of the variances will imply that this series of random variables must converge almost surely. but we have already pointed out that the truncated random variables themselves are summable in the sense of almost sure convergence in this sense. So, therefore, by combining these two series, we immediately will conclude the series of real numbers formed by the corresponding expectations must converge, and therefore, for all C positive we have established the three necessary conditions, and this is completing the proof of the 3 series theorem which we have discussed earlier. All right. So, we move on and see some further applications of weak convergence. So, to state this type of applications that we are going to consider, we recall some earlier results from week 4. So, we have discussed earlier that the continuous mapping theorem holds for convergence in probability. To be more specific, if we have a sequence of random variables converging to x in probability, and if you are given a continuous function g on the real line, then look at the sequence of random variables g of x n. The statement says these also converge in probability to g of x. So, this kind of statements we have seen earlier in week 4, but now we are interested in the rate of convergence of this g of x n converging to g of x, and these kind of results are typically called delta method, and these are very useful in practice, because if you have some information about the original sequence x n converging to x in probability, you can derive a rate of convergence for g of x n converging in probability to g of x. So, let us see. So, this is the statement of the delta method. Again, we do not prove this, we are going to apply this result to obtain some nice rates of convergence. So, this is the setting that we have a sequence of random variables such that a priori we know that for some b positive and for some real number a, the n to the power b multiplied by x n minus a, these random variables converge weakly to x as n goes to infinity. So, this is the assumption. But now, we are saying that if we now take a nice function g, nice in the sense that it should be differentiable at this specific point a that we have chosen, then the result states that with the same rate n to the power b, g of x n minus g of a converge to a specific limit, which is given by g prime of a, which is some scalar multiplying the original limit capital X, and this limit is in the sense of weak convergence as n goes to infinity. So, this is what is known as the delta method. In particular, we are going to be interested in the results in the form of the central limit theorem. What we do is that we go back to the classical central limit theorem or the Lindeberg-Levy central limit theorem and combine the delta method statement that we have seen here, and we are going to obtain some nice rates of convergence. So, what is the result? So, let us see. What we are saying is that, let us say I go back to the classical central limit theorem. So, there we need to consider a sequence of IID random variables with the assumption that the variance of the random variables are positive. So, denoted by sigma squared. Now, bring in a nice function g, which is now differentiable at this specific number, which is expected value of x 1, and we additionally will impose this condition that g prime at the expected value of x 1 is non-zero. Then what happens is that you look at these centered and scaled random variables that you multiply by square root n, but look at g of x n bar minus g of x 1 divide by the corresponding standard deviation, that goes to g prime of a times z. So, strictly speaking, we are making the choice of a as the value expected x 1. Okay. So, that is the idea that we are applying here. So, we are combining the delta method together with the Lindeberg form of the central limit theorem. So, here of course, the random variable z follows normal 0 1 distribution, and the convergence we are stating is in the form of weak convergence as n goes to infinity. So, let us see a quick application of the delta method that we have just stated. So, what we consider now is a sequence of IID random variables. More specifically, assume that all of them are normal 0 1 random variables. Now, look at this nice function g of x taking the value x squared plus small x for all small x in the real line. Now, note what is g prime of x for all small x, this is 2 x plus 1. In particular, if we now evaluate this derivative at expected value of x 1, which is by the way 0 by our assumption. So, this g prime is nothing but 1. So, if you appeal to this delta method, what we are saying is that look at these quantities x n bar squared plus x n bar, subtract out the corresponding contribution from the function value at expected x 1. So, that is this term here, and divide by the standard deviation, which is sigma equal to 1, and multiply by root n. As n goes to infinity, in the sense of weak convergence, they converge to a normal 0 1 random variable. So, this is a nice application of the central limit theorem together with the delta method. So, in this lecture, what we have seen are some nice results involving the weak convergence. More specifically, we have talked about the Slutsky's theorem and the delta method, and we have also combined with the Lindeberg form of CLT or the Lindeberg-Levy form of CLT to obtain other nice results. In particular, we have pointed out that the Lindeberg-Levy form of the central limit theorem is a stronger result than the weak law of large numbers. We stop here. Thank you.